Okay, so this week we're gonna get into chapter 11, work sampling. Some people work sampling together. Some people don't write it. In this book, we don't write this together. So you go work sampling. So work sampling is nothing big. It's just a random sampling. We're gonna base that on scientific theory and laws of probability. Again, probability review is if you have an event, we're looking at every possible outcomes, okay, everything that can happen to that event. So you have to think 360 degree around. And work sampling is subdivided into 4 techniques, sub-techniques. So that's one elemental ratio, and the second one is your performance sampling, and third one is your time standard development, and the fourth one is your process effectiveness. And they're all studies because we are recording an operator's action, okay, all the operation. So elemental ratio study, so each activity must be measured and then compared to the total time. Okay. So if you have an element number, so one student asked me what is element. So element is nothing but the lowest or the smallest unit possible for something. Okay, so if you think about chemistry, we have a system, we have organs, and then we have going down all the way to compounds and then the element. Okay, so your atoms, and for chemistry we cut it out up to quantum level, and then quantum and all the way down is divided for the physics. Okay, so when you come back here and if we applied it for big things like operation, we're talking about the work element. So element is nothing but if you take a look at an operation and you divide the operation into different parts, and each part we call the work element. Okay, so what we do here in elemental ratio is we're gonna measure each activity, and then we're gonna compare that activity, each activity of an operation to the total time of that operation. So if you think back your previous lab series, you have the entire production, your mock assembly line, and then you have your workstation for them, including 2 other parts, which is your receiving and shipping. Okay, so these are all the work element of the operation. So this is a elemental ratio. It's nothing but a ratio. A ratio is nothing but something divided by another thing, and you're looking at if A is divided by B, your ratio is A is to B, okay? And the value of A divided by B is also called a ratio. So an elemental ratio study will determine the percent of time that each element of work takes. So elemental breakdown and ratio estimate. So we start the study by listing the elements of work. So here in this work, we have 7 elements. Okay, then we estimate the ratio. So here in this table, we're just showing the estimation of all of that 1 to 7 element of work. So here, work element 1. So what are we doing for that part? We're loading and unloading. 2 is your machine time. 3 is your setup. And 4 is your tool change. 5 is your inspection. And 6 is your material handling. And 7 is just being away and idle time. Okay? So altogether, we have estimated each work element. These are just estimation. Okay, those are your ratios of 20, 35, 15, 7, 5, 4, and 14. So those are our estimates. If you plus all of them, okay, add them up, you're going to get 100%. Okay. So now we're going to take a look at productivity. So from 1 all the way to 3 is very productive. From 4 all the way to 6 is productive, but you have a delay allowance with it. And then number 7 is totally away and idle, so therefore it is totally non-productive, and that's your 10% in allowance. Okay, these are counterproductive, but then it also has a delay time included in it. Okay, you can extract the delay time out of it. Alright, so example, we're going to get into a list of elements for a machinist's job and the estimated elemental ratios. Let's take a look at it. So percent allowance, we're calculating weight and other 14. Then we have material handling, inspection, and tool change. They have delay allowance with it. So that's 4, 5, and 7. So altogether 30% is your percent allowance in total. So work element, we're going to take a look at it. So here's your percent allowance divided by percent productive. So 30% allowance. So 100% minus 30% is your productive percent. That's 70%. So 30% out of 70% work. So 30% allowance out of 70% work. Or you can also say 30% allowances divided by 100 minus 30 is your 70% productive. It's going to give you 0.4286, and that's a 42.86%. Okay. So we use these estimates to determine the total observations needed for a specific confidence level and accuracy. So accuracy is nothing but in operation we met on. This measures the closeness of the ratio to the true ratio of an element. Okay. So every time we think about accuracy, you're always comparing your data to a standard. So here the same thing, you are looking at your data, which is your ratio in this case, and how close that is to a true ratio. So this is your standard, okay? So you're looking at your data, which is your ratio, to a standard data, which is your true ratio of an element. And that is how you determine your accuracy. Another thing is your confidence interval or confidence level. So with more observations collected every day, because in the plant we collect the data every day. Okay, some people don't even know that we're collecting the data. So in a study, because we don't want to disturb their work, we want their work as natural as possible. So the ratios are more consistent and confidence level grows. So if your ratio is more consistent, your confidence level is going to grow because you become confident to be able to determine the work element. So we usually think how many observations we need to collect to achieve a specific confidence level. So every time we have to determine a confidence level for an operation, we always look at the past data and then we estimate, okay, the confidence level that we're comfortable with. So in any data collection and study, we do best to keep 96%, sorry, this is actually 5, that's my typo. That should be like 95% confidence level. So 95% confidence levels means that our data, so here elemental ratio, okay, they are accurate 95% of the time. So it means that you are confident 95% of the time your data, so here in our case, elemental ratio is going to be accurate. So the remaining 5% of the time, so our data will be off of with some reason. Okay, so these are we call it error. Okay. Alright, so sample. A sample is an observation. It's just an observation of an operator's work in a facility. So in this case, of an elemental ratio. You can apply this to small business too, okay? Small businesses that are producing some small products like furniture and fabrics and things like that. Okay, so if you observe 100 operators at once, you get 100 variable samples at once of different operators. You can also take, like, if you observe 100 times of one operator, you also get 100 observations, but of that operator. Okay. Randomness is based on chance, and it is mandatory in sampling. Why is it mandatory? Because we have to reduce the biasness. If you have bias in your data is not going to be good. Okay, it will be completely leaning to left or right. So randomness can be developed many ways. The first one is we do random number tables. Second one is we do random number calculator button. You touch the calculator button, and it's going to give you a random data. You can also draw in Excel. So drawing numbers from a hat, that's a manual thing. Long time ago they do it using last 4 digits of telephone numbers in a telephone book. Long time ago they do it. These are deprecated 3 and 4. Okay, right now we usually use the Excel to run the random data to select some samples. Sample size is nothing but the number of observations. So the sample size is the required observations for a confidence interval. So we use this formula to calculate sample size. So n is your number of observations needed, and z is just the number of standard deviation. We usually get that from a table. And p is your probability, that's the percent of the total time that employees perform one element of work. A is your accuracy that you desire for that operation. Okay. Example, what's your sample size do we need? How many observations for plus or minus 5% accuracy, and we have 95% confidence on a job that accounts for only 4% okay, of the workday. So we're going to use the confidence level. If you see CF.L, that means confidence level table, which is this little one, to get Z value, percent confidence, which is your C. So we are looking for the sample size. Okay, sample size. Now we're going to get Z out of the table. That's your confidence level. We take a look at it. The question said 95% confidence. So therefore right here. And your Z is at that time 1.960. Okay, and we're going to put that. Your P, they said, account only for 4% of the workday. So therefore, we're going to go 4%, translate that to decimal. So that's 0.04 for your probability, okay, of your work. And then A is going to be 0.05, is your 5% accuracy, which is given to you right here, plus or minus 5%. Sometimes they're not going to give you directly by saying plus or minus 5% accuracy at all. They're going to give you, error. So if you get error plus or minus 5% in your question or in a situation, you know that means A is 0.05. So we put them all together and then calculate it by using your calculator. And you're going to get 36,879.36. And then you're going to round it, okay, to 1, 2, 3, 4, 5 significant figures. And you're going to get 36879 observations. So that's your sample size. Okay, this is just a review for your probability and normal distribution. Like I say many times, the data out of the nature. The data where we take most of the time when you plot it is always kind of like a bell shape. Okay, so meaning the average is concentrated at the center. So this is your central tendency, your mean right there. So therefore, and all others are going to spread out. Okay, from the mean out to this side and out to that side. And if you find yourself right there, your data, that's the outliers. And we usually eliminate outliers so that it won't affect the data, okay, majority of the data. So the normal distribution curve is used to describe the laws of probability. So every time we take a look at this graph, the area is, okay, the area underneath of that curve. Okay, so that's we call that the acceptance area. Okay, so from here to here, you have already understand your 1 standard deviation, 2 standard deviation, and then 3 standard deviations. Okay, those are your acceptance level right there. So this is just a review for your normal distribution. So here I'm going to start examples, many examples to see work sampling. So here that's your percent of your work, okay, and we calculate in this case. So here you have observation in 1, and that's when you add them up, you're going to get 82, okay. So if you add 1 plus 5, 10, 15, 20, 15, 10, 5, and 1, it's going to give you 82 total, okay. And you will try to get the percent of each, okay, of your observation. So here, number 1 is 1 divided by 82 total times 100, where changing this decimal into percentage. That's why we multiply with 100 and you get 1.22%. And we do the same thing, and the second one is 5 out of 82, so you get 6.10%. So this is how you calculate your work sampling, okay? And here, this one you have a 95% confidence, meaning like most of your data, majority of the data is going to be from here to here. Okay. All right, second one, percent, you see that? So 2.78, how do we get that? So altogether, number of ways is from 1 all the way to here. We add them up, 1 plus 2 plus 3, 4, 5, 6, 5, 4, 3, 2, 1. Okay, when you add it up, you get 36 total. So 1 out of 36 is going to give you 2.78%. Okay, 2 out of 36, 5.56, 3 out of 36, 8.33%. And then we do the same thing. Since this is like a mirror right there, 6 in the center is 16.67, and you have 5 on each side, 4 on each side, and 3 on each side, 2 on each side, and 1 on each side. So therefore you can see how beautiful your normal distribution is, okay? So when you take a look at it from here to here, again 0.95, that is your 95% confidence, okay? Zone right there. So anyway, you know how to calculate the percent work sampling, okay? That's how we do it to see each part of the work, okay? And if you take a look at in terms of probability, this is everything that can happen. And you're gonna roll your dice here. In this case, you're rolling the dice again and again. You roll the dice again and again, again and again, again and again. After so many times rolling the same dice, it's going to give you that type of normal distribution, and it will come approximately the same ratio, okay? So that's the magical about this world. So anyway, like that. So here we go. The third example. So here is the oil canning line work sampling study results. So when you look at it, we can now identify the work sampling is right here, the data are, okay? So observations, again, 2,500 observation for work, 1,500 observation for either, and so and so setup, okay? Setup, material handling, quality control, maintenance, and bad material is in this oil canning line. So you have all the different work. So we added up and we get 7,400 observations for all of this work, okay, element. So when you calculate the work element for each one of them, you get work for out of total is 33.78% we're doing. Idle, you're idle 20%, that's not very good. So if you want to go lean, you want to eliminate this, okay, time. And then you're going to increase that. So therefore, or this or this or this or this. Okay, setup also need to be reduced to 800 out of 7,400 observations, and you got 10.81%. So we have 6, 4, 7, 17% for all of that work element. Okay. Calculation, the same thing. Each work element divided by the total times 100. Change that decimal into percentage, and you're going to get 33.78%. All right, the next one. So here is a tally, and they're just trying to get the data for 40% transport load in work sample for your truck, and 40% transport is empty. So this guy just record the data that way, and 20% is going to be idle. I'm going to translate that into work sampling. So we get 72, 63, and 57 for each work element, and the total is 192. Okay, so when you calculate the percentage, we get 72 out of 192 times 100 will give you 37.5. 63 divided by 192 times 100 is going to give you 32.8. 57 divided by 192 times 100 is going to give you 29.7. Okay, so that's your percentage for your work element, 3 of them in this case. The next one, so work sample 2, crib 11, 18, okay, that's just your date, and we're going to study all the way to 12/10, blah blah blah, that's your date. So we're running about a month, okay? So 11 is November, 12 is your December, starting from November 18 all the way to December 10, so that's a month. So if you take your 8 days off, so that's your weekends, okay? So anyway, So number waiting at 2 crib window 0 all the way to 5, so 1 2 3 4 5, and that's your element of work. Number of observation for each element is going to be that. The total is 1533. Therefore, for each one of them, we can get work sample. So 350 divided by 1533, you're going to get 22.8. We want to do the same thing. Okay. Now you get a hold of what work sampling is and how we calculate. It's a very simple, okay, high school math. So 350 divided by 1533 times 100 is going to give you 22.8% right there. We do the same thing for all of that. All right, the next example is the results of the satellite maintenance sampling. So all the satellite right now, they're smart. I'm trying to make it smart. A long time ago, ancient satellite are not smart. But right now, we're trying to make the satellite maintenance smart because the machine got to fix itself because you cannot accompany the machine all the way out into the planet, okay? Because it's so far away. So it costs a lot of money. So therefore, we're adding logic to the machine to make it smarter so that they can fix themselves. And you don't have to accompany the machine to fix it, okay? So human life will be safe and we will be sending a lot of machines into the universe, okay, to be able to understand what that is about. So elements here, maintenance, work, idle, 3 of them. We do the same thing. Observation is what you observe out of your facility, and then you're gonna write that down, 875 355 307 for these work elements, and you get the total 1537. Okay, this divided by that time 100 is going to give you the percent of that work. So therefore the sampling is 57% for maintenance, 23% for walking, and idle is again 20%. So if you want to boost your efficiency, we're going to push our plant, okay, to reduce that, okay, 20%. So you can reduce 10% of that idle time and increase the other two, okay? So this is how you make profit. And if you're a good manager and data analyst, you're gonna reduce like 2% each. So that's what I would do. So that way you're gonna save about 18 for yourself to improve in a later date. Otherwise, if you improve everything, there won't be anything to improve anymore. So that's just kind of like getting rid of your own survivability from your company. So make sure you go slow, okay? In your improvement. So therefore, you can do continuous improvement at the same time increasing the profit for your company. All right, so the next one is your work study study of plant. Okay, week ending November 19, blah blah. That's your year. So element we divided, and we have only 2 elements right here, working and not working. So our lab also have only 2 elements, the idle and operating. Okay, for each workstation. So here the total is 1375 and then 1000, and your total is 2375 for 2 work elements. So here we calculate the work sample percent, and that's you get 58, and this one is 42. We're going to stick to the same formula, which is really easy. Okay, each divided by total times 100 will give you each percent. Alright, the next study is your performance sampling. So in performance sampling study, in this study what we do, we observe, and then we're going to rate the operator's performance. The operator performance is productive operation only, okay? If operator is not performing idle or just resting, okay, or within his allowance time, that won't be productive, that would be non-productive, okay? So here is, we're just going to rate the operator performance, and that's your productive operation only. And we record the speed and tempo of that operator. So what are we rating? We're rating the speed, we're rating the tempo. So in our lab, we have the speed, but the tempo is messed up. Yeah, none of the tempo are the same. So tech time is we're trying to make the the workstation speed the same. Okay, in our lab for group 1 and group 2, we don't have that. Okay, just the tech time is completely failed. You have your own tech, and none of your tech is matching. Okay, so it's not very good assembly line, but then you get an idea, okay, for a short moment of study within a semester. Okay, so observation of an operation with 4 elements of work is right here. And we have 4 elements like packing, load, hoppers, away, and idle. This is productive, and that's not productive. Okay, and this recorder is telling this all of these observations. So we do not rate non-productive operations such as away and idle. And we can tally to check observation of each work element backpacking in load hoppers. So here we go, table 11.3. So when you take a look at it, you're going to see the backpacking, a number of observation, that's your raw data. Leveled observation is we adjusted by taking out some other allowances. Okay, so anyways, 82 rough raw data, and then 75 leveled. And then load hoppers, you have 13. When you level the observation, we get 12.5. And your C is away is 7, and then your idle is 20. Okay, so therefore we're going to start the total observations is your 82, your 13, your 7, and your 20 for your 4 work element added up, and you get a total of 122. So now we can get into percent work sampling. 75 divided by 122. So this 75 is a good one because we leveled our observation. So leveling is nothing but level observations are they're comparable to your normal time because we're looking at the percent times number of observation. Okay, so here we get 12.5. Okay, that's for your load hoppers divided by a total 122, and you're going to get 5.75%. Then your idle, away is going to be 7 divided by 122 is 5.75%. Sorry, 12.5 divided by 122 will give 10.25%. And then your idle is 20 divided by 122 here is going to give you 16.4%. Altogether will give you 100%. Okay, so there we go. Percent productive 75 plus 12.5 divided by 122, we get 71.7%. Okay, so here this one, and then that one, okay, divided by our total, okay, and that is going to be 71.7. Average rating of the first productive work is backpacking, so that's 75. We choose a level 1 divided by 82 is the raw data, is going to give you 91.5. Average rating of loading hoppers, so 12.5 leveled divided by 13 is going to give you 96.2%. Okay, this is another example. So after studying 1 month, 5 workstations, doing 4 elements of work in backpacking operation, 825 hours of labor was used. Calculate how many hours were spent on each element of the job. So in order for us to calculate how many hours were spent on each element of the job, we do the same thing and we take this work sampling, which is 61.5% we spend for backpacking, and the 10.2% we spend for load hoppers, 5.75% we spend being away, and 16.4% we spend for idle. Okay, so altogether 93.9 efficiency loss is 6.1%. We lost it. So when you calculate all of that, you're going to get 100%. So right now this is just a realistic number because you always have efficiency loss. All the example that you saw before this does not include efficiency loss. So that's kind of like a theoretical calculation right there. But in real life outside, you will always have efficiency loss for every machine and every operator. Okay, sometimes they combine the operator and the machine if they have to operate that together. Okay, so it depends on your design as well. So anyway, so back to how to calculate the hours. So for each work element, how do we do it is we multiply, okay, this percent translated into decimal. So 61.50 is 0.6150 times 825 operation hours, okay, for that work element. So you will get this much of hours. We do the same thing. Translate this to decimal 0.1025 times 825 hours, because this is given to you in your questions. Okay, so every time you read the question, don't go like I do. I go real fast because I've read this type of question so many times. Okay, so you go slow, and then you read slowly, and then here 825 hours of labor was used. Okay, so right there. And then you also don't have to worry about it because this is your first time doing it. And if you get into our line, you'll be doing it again and again. So your brain will automatically get it. Okay, your brain is you anyway. So 0.0575 times 825 hours going to give you 47.44. Then here it's going to give you 135.30. So when you take a look at it, we're already spending 100, okay, 170 around, okay, 180, let's say 180 hours being away and idle. So those are the points that you've got to play with in order for you to be able to increase the efficiency of your productive, okay, operation time. So that's how we play with, and the mathematics is super easy. Okay, you will do this again and again and again, and then you will definitely get it. So don't worry about it. So here just we're trying to write the entire time standard. Okay, so that's hours used divided by bags pack is equal to, so that's hour per your element, work element. So therefore you have 507.38 from here, okay, plus 84.56 hours, okay, divided by 35,392 bags, okay, which is given to you right here. So equal to, you're going to get 0.01673 hours per bag, okay. So that's your hours per unit, okay. So here hours per unit, the one that we're always doing in operation charts, the same thing. All the charts are very similar to each other. We're always hitting hours per unit, hours per pieces, hours per. Here in this case, your unit is bags pack, so bag. So 0.01673, okay. Plus, we spent 10% allowance, so that's 0.00167, okay. 10% is nothing but you just here 0.01673, okay, 10%. So therefore it's going to go down one decimal. Standard time is 0.01840, and then your bags per hour is 54. You know, one student always asks me, how did you get this? When you flip it, you flip this one. When I say flip it, this is 0.01673 hours per bag. So when you flip it, you got bag divided by 0.01673. There is 1 in front of bag. Okay, if there is nothing with the bag, that means that instantly you know there's 1 hidden 1, okay, next to the bag in front of it. So therefore 1 divided by 0.01673. Okay, so that's how we do. So in this case, our standard time here is this allowance and that allowance. So therefore don't forget this allowance to add it. So first you're going to add 0.01673 and then 0.00167. Add this. So you will get 0.01840, okay, and that is your hours per bag. So your unit is the same here and here, the same unit. So therefore 0.01840 hours per bag. Flip it. 1 divided by 0.01840 is going to give you 54 bags per hour. Okay, so I don't know like why you guys don't want to sit down and calculate it, okay, and then put the blame on other people all the time. You have to sit down and you have to take your pencil or your pen and you have to take your papers, and then you definitely need to calculate it. Okay, you got to do it at least 1 or 2 times in order for you to get it. The reason for asking how did you get it, how did you get it, is because you didn't do that. Okay, simple as that. So don't ask me questions again and again. Okay, I already told you to calculate this, and so many times I told you to flip it. Flip it, meaning you have to flip the ratio, saying you gotta understand how did you get the standard time. I don't know how to explain more than this. You have to add this and that together because you're not just working, you're still idling. Okay, every time you work, you go to the coffee shop and then you drink, that's also idle, being away. Okay, idle. You come back and then you work. So we calculate all of that in our operation. Okay, so if you're at the operator and doing something, your manager is always watching you what you're doing. Your work time and then your work time, your idle time, and your time away from that workstation is 24/7 recorded. So that's therefore I try to tell you so many times, we always forget about the camera around us. Okay, there is a camera. There always is a camera, so don't do the silly thing. At all, as soon as you get to your work and you get the job and you start to work, you have to know that you're being watched 24/7, especially in a manufacturing plant and facility. Okay, because you're dealing with so much money. Okay, so much money, expensive equipment around you. Okay, everything that you touch is valuable. So therefore, your time, work time, and then your idle time are always calculated. Okay, so therefore you add this, and that is your standard time. Okay, got it? And we call the whole thing time standard. So time standard is not this, not this, not this, and not that. Time standard is everything. Okay, so from here, here, and here. So don't ask me ever again. The same thing. There's only 3 major unit right there. Okay, I mean, shouldn't say unit, values right there. The first time is your work. The second time is you not working. And the third time is you working and you not working total time. Okay, and that's your standard time. And then you flip that. Okay, hours divided by bag, flip it. Flipping the ratio means bag divided by 0.01840. Okay, hours. Bag has a 1, hidden 1 right in front of it. So 1 divided by 0.01840 is going to give you your 54 bags in an hour you got to pack. And if you go down under 54, meaning that you're not working, okay, because you are lower than the average production, therefore you will be on a layoff list, okay. And if they find a new operator that is going to produce within the standard time, you're going to be laid off. So that's how it works, okay. So therefore you have to be so careful about all this time standard, and it is your responsibility if you get the job in this field to calculate that. Okay, you cannot go and get rid of an employee because how you feel about that person. Feeling doesn't count. And those who are using the feeling to destroy someone else's life, because job is a life, okay? The operator has a family, they have everything on people who are depending on that person's income. So therefore, every time you think about laying off the employee, you have to sit down and really think about it, okay? And you will not decide with your feeling. Never do that, ever. You're going to decide with the facts, okay? And you're going to decide with the data that you have recorded. And these are your evidences. And these are going to protect you if that employee go against you in the court. Okay, so therefore don't take your job lightly, and you always have to take your responsibility. I'm trying to tell you since this time you're in the school to be careful about these things. Okay, never ever take this not serious, because this is serious. Your action can cost someone else's life. Okay, so therefore you will do your job and you will calculate all of this if you're going to be staying in this line. Okay, so take it seriously and please study. Okay, so the next study is your time standard development. So we're going to use the work sampling again to develop time standard quickly and effectively. So example, a maintenance department or it was work sample. Okay, we're gonna sample the maintenance department with the goal of setting time standards to a level 95%. We want to raise it. So plus or minus 5% accuracy on 3% elemental ratio. Okay, that's your probability jobs. And then the resulting data was collected and is summarized in a table 11 4. Okay, don't do like I do, because I read this really fast because I've done this so many times. Okay, similar problems. You in the exam, you're gonna read it slowly. Okay, slowly, and try to get everything in your head. Okay, so table 11 4. So here we get that. So you have your elemental number, so that's your operation work, and you are dividing the work. Uh, I shouldn't say dividing the work. Okay, put the element work of that operation into numbers. So you have 8 parts in that operation. So jobs are in the maintenance department. Okay, operation. So job description is you have millwright, you have welder, electrician, and machine repair, carpenter, walking away, and idle in this department. So number of observations is nothing but your number of observations resulted from the observations over a 1 month period. So that's your study time is a month. And then we have ratio percent is your B. So that's your ratio percent, the number of observations of one element divided by the total observations. So all total observation is 50,000, and you have 1 to 8 work element. So the first one is a 20,000. So that's okay divided by total is going to give you 40% times 100. Yeah. And then here is somebody forget times 100. So anyway, see hours is the same thing. Your total hours for the 1 month study were made available from your payroll. Okay, that's from. So 3840 hours. I'm gonna fix all that typo later. That's just my computer spitting out all the typo. If I go like instead of R O, I go O R. So anyway, so you can fix the bar as well. I'll fix it in the handout for you. So anyway, so this ratio, so that's how we calculate this divided by that, and you get that, this divided by this, and then you get this, and do the whole thing, yeah? Okay, so then we use the table 11.4, and then we're going to extend that to table 11.5 to develop the time standard. So first thing, we're going to take the productive work element, so get rid of work in idle time, so 1 to 5. Our hours here and the work order is going to come off from your maintenance department. And then your full is you're going to calculate the hours per work order. Okay, hours per work order, the same thing. Hours per unit, the same thing. Here it's always changing your unit, your pieces. Okay, and can come in any different kind of name, but the same thing. You have seen this again and again. So it's going to be 2 divided by 3. Okay, so that's 2 divided by 3. So what we're doing here is 1536 divided by 825. In this example, it's going to give you 1.86. So that means 1.86 hours spent per work order for work element number 1. Yeah, and then you do the same thing, and you're going to get all these values. Okay. Then we're going to come in and add our percent allowance, the same thing, plus percent allowance. So that's your 15%. And never ever forget that little plus sign. Okay, you get the standard time. And the student always come and ask me, how did you get the standard time? You add that too. Okay, you add your hours per work order or hours per unit, hours per pieces, plus it said it so, plus, and then your allowance. Okay, so don't, when you read it, try to recognize what you're reading and don't just read it and let it go. Don't let it go. Plus mean plus, plus mean you add it. Okay. So when you add it, you are going to get this, which is 2.14, because our allowance is going to 15%. So therefore, if you work 100%, okay, your work is a 0.15, that's 15% allowance. So you can time it and get this. So this is me, I go this way, but you can also do the traditional way, which is 1.86 is your work element number 1, plus we're going to calculate the allowance because it said it so, 15% allowance, so therefore my plus is there, so that's your plus, and then 15% of this, so therefore 1.85 times 0.15 is your 15%, so therefore you're going to get the 15%, we add it, it said it so, please add it here. So you get 2.139 rounded up, and you get 2.14, okay? Because 9 is over 5, so therefore when you round it, you get 2.14. Do the same thing for the rest of them. So that's how you get your work hours per hour. Again, work order, sorry, per hour. Yeah? Okay? and then flip the ratio. Because this is hours per work order. When you flip it, you're going to do 1 divided by 2.14. It's going to give you 0.47. Yeah, that's it. So here, number 6, work order per hour is calculated by dividing 1 by standard hour, and you get that. Yes. So I told you to just do the lab, okay, and then fill it up. And please wait for the later chapters for the explanation, and you can do that. You want to know. So anyway, so now you know how to do it. So step by step for the lower part of your operation chart or any other chart. Okay, we will go over it one by one. Okay, so table 11.6 is showing you the data collected. Okay, so this is your data collection sheet. So here are the same thing, your work element. So this is your work sampling data collection sheet. And they usually go by tallying right there like that. Okay, little mark right there, because it's easy to do that way. And then you're gonna sort out your non-productive, and then you go your total observation and then percent performance, and then you're going to add your 5% allowance, and then you're going to get 70% is your standard time. Yeah. Okay, so table 11.7 shows a summary of the study after a month. So we take the data a month, and then we're going to show that in this table. So here you get the summary of work sampling data after 1 month and time standards. So blah blah blah. So number of observation, we have observed 14,100. And then you do the same thing to calculate each of that, okay, percent of total, blah blah blah. So in real life, you're gonna get more complicated, okay? So you have many different work elements right there for you to calculate. And then in our day, you don't have to be so panicked, because you will definitely get something that is already done by other person in front of you, okay? So therefore, you just go with the flow. And most of them, 80% of them go with the flow. So 20% try to do their own, and then they benefit from that because the environment always changes, the operator always changes, so you can stick to someone else's work forever, okay? So anyway, so that's how you calculate your work sampling. And here is your hour, here is your unit produced. We do the same thing, hours per unit, and then you're gonna add your allowance, and then you're gonna flip it unit per hour and calculate that. Okay, you should be able to do that by now. So the last one is just an example here. This is your process effectiveness study. In process effectiveness study is used to evaluate operation. We always use the Fred Myers and Associate because the textbook itself is written by this guy, okay, long time ago. So it's used to evaluate operation, process, or plant. So during the study, information is collected about the type of work being performed, so the amount of contribution to core processes, and then the operator pace, speed. Okay, so example here, you can refer to the example on page 3. It's the same thing. We're trying to get PZA, okay, and then your sample size, and then your confidence interval depends on your data set, okay, previous data set. So anyway, I'm not going to ask you about this. If you know a little bit of that, we're okay with that. Make sure you get how to calculate the time standard, okay? Okay, so that's it for today.